the title of the talk is Why Use Computational Models and Methods to Model Evolutionary Game Theory. And the more obvious question maybe is, why game theory? Okay. So why game theory is kind of very profound, because game theory describes how well decisions are, how well they suit you, what they give to you. And decisions are made in basically every possible sector of science. I think the most prominent one is this example in the handsomeness of cooperation. You have to make a decision about whether or not you cooperate or defect. This is for social science, it's interesting. But it's becoming interesting for multicellularity, for biofilms, for cancer, for social interaction with these monkeys. If you want to evaluate what actual games do, you need game theory. It's important for economics, psychology, or if you think about taxes or these kind of situations, politics, they all deal with decisions, and therefore they can be described by game theory. That's why we do game theory, because it's a very fundamental framework. When I said it's about decisions, well, then you have to have options that you can choose from. In its simplest form, you have two options. If you have one option, then that's not an option, that's a default. So you have to have these two options you have to choose from. And then these two options are associated with some kind of effect. And these effects we call pairs, because it's something that you get. Well, in the simplest game, if you look at it, you choose option A because you want to get $4 instead of $2. Or maybe the value is too low and you don't care. However, you choose one of these options and there's an effect coming. Well, this is really simple. The situation becomes much more complicated the moment you have more than one player. The moment you have two players. And when you have two-player games, what usually happens is that you have two players ask independent what of the two choices you're doing. And then let's say both players answer, we have choice A. Okay? If both players use choice A, and I need my mouse here, then both players will receive the $6 pay. You always read this table to the left. Okay? So the player that's on the left receives what's in this matrix. If both players decide to choose B, then both players would receive 2. If they choose A and B, well, then the player who chooses A gets nothing, and the player that chooses B gets 10. Very easy. The interesting thing is, if I don't know what the opposing player does, well, then it becomes tricky. Okay? If we both choose A, then we get both $6, which is in total $12, which is nice. However, if I choose A, and the other player says, hi, you're going to choose A, I'm going to choose B, I get 10, you get nothing. See that suddenly becomes some kind of dilemma. So I'm going to talk about these matrices a lot, but again, remember, it's about choices. The payoff is the role player, which means the player on the left gets this. And this entire matrix is what we call a payoff matrix, and I've written this within E. Don't worry, we're not going to go too much math here. But in its general form, we always try to bring this matrix on the left in such a way that we have zeros on the diagonal. You can do that by either applying mathematical operations on the entire matrix or on one column. So on the right, you see that I first applied a -6 on the left column, and then I applied a -2 on the right column, and then suddenly I arrive at a matrix that has zeros on the diagonal. We always sort of form all these matrices we have in such a way that we have zeros on the diagonals, because then suddenly they become comparable on other matrices. Now, there's a big difference between a single player or two players making choices or populations of players making choices. Right? I mean, if it's just two organisms or two players, I just look at it and see what's going on. However, if there are groups of organisms that make decisions, well, then suddenly the outcome of these games depends on the frequencies. If there are lots and lots of A players in this pie chart, or actually the B players, well, then I'm going to encounter on my choice here more B choices. However, if there are lots and lots of A players, well, then I can expect that lots of organisms choose A. And then it's a different case. So suddenly the frequencies of players matter. What we always assume here when we do this simple sort of transition from a single player to a population of players, we always assume that these players are so-called pure strategies. That means that an A player will always deterministically, under all circumstances, choose the A choice. And a B player always chooses the B choice. That's why they're called pure strategies, because once they determine what they're doing, they're sticking to it. Okay? Now, you can just compute the fitness of pure strategies rather primitively or rather easily. I'm going to talk you through that. If you are an A player, there's a certain probability that you encounter an A player, and that's dependent on the frequency of A players. And the payoff you get is this E of AA, which means that the payoff that you have is your base fitness, which we usually ignore, plus the frequency of A's times the payoff that you as an A player get against playing A, plus the frequency of B players times the payoff that I get against the B player. Now basically we consider this first rule. And the same is true for the fitness of the B player. The payoff of the B player is the frequency of A players times the payoff that the B player gets against an A player plus the frequency of the B player times the payoff that a B player gets against the B player. It's a player 15 times. Okay, so rather simple how to evaluate them. Once you know these fitnesses, well then you can say which of the two strategies is better, because that's the one that gets more payoff on average, and which one is the worst strategy. Now, interesting enough, when we get this into this normal form, or this general form, we have only zeros on the diagonal and all the other things on the off diagonal. The only thing that matters for these games is the sign of these values on the off diagonal. It only matters if they are plus or minus. The real values in the end don't make any predictions about who the winner is. So let's look at the different cases for these matrices. Let's look at the top left one. If I'm an A player, well then the frequency of other A players doesn't affect me because I get 0 from them. However, if there are lots and lots of B players, that's really bad for me because I get negative payoff from them. So the first row says us A players suffer when there are lots of B players. The second row says if I'm a B player and there are other A players, well I benefit from A players. And I completely ignore B players. So what we have is a situation where A's suffer from B's and B's thrives on A's. If that's the case, then we'll remain or we'll end up with only B players and no A players. Okay? So in this particular game, B players, and it doesn't matter how high these values are. It will always be that case. The only thing that changes is how fast they arrive at that solution. Okay? Now, the other matrix, the top right one, is just inverse, right? So if there are lots and lots of B players, A players thrive, and if there are lots and lots of A players, B players suffers. It's just inverted. The A player wins in that situation. Well, oops. How about this thing on the bottom left? If both payoffs are negative. If there are lots and lots and lots of B players, well, A players suffer. If there are lots and lots of B players, if there are lots and lots of A players, B players suffer. That means that those players that in the beginning of the situation are more abundant are the ones that suffer less. Okay? So if I have, let's say, a ratio of 90 to 10 A players, the B players will suffer much more because they encounter way more A players than B players. The result is that both of these strategies can end up winning, but it depends on the start condition. If I have lots of A's, A's will win. If I have lots of B's, B's will win. The situation where both strategies are good, but the outcome is determined by the starting condition. The opposite is true for the bottom right situation. If I have lots and lots of B players, A thrives, and if I have lots and lots of A players, B thrives. This is a little bit like Lockwood Terra, foxes and bunnies type of situation. If lots and lots of bunnies, foxes thrive. If lots and lots of if I have few bunnies, foxes are not that well, then maybe I have these balances. So what happens in this bottom right situation is that none of the strategies will actually outcompete the other one. They are both stable at the same time, and they will go to some kind of equilibrium. If they would get the same payoff, they would end up at 50-50. Here, this is the only case where these values matter, but not qualitatively. It's just at what fraction they equilibrate. Now, all these red boxes that I just counted are what's called evolutionary stable strategies. And there's a general way of defining evolutionary strategies, and it's sort of just two rules that you have to remember if you're in that. First of all, I created a matrix with 3 players, and all these values in this matrix must be constant, otherwise you can't do that. Okay? The first question is, you ask if I am getting the highest payoff in my own column. So the A player gets playing himself 1 as a payoff. And then I just ask if this is the highest number in its column for A. It's higher than 0.9, it's higher than 0.1. That means that this A player necessarily is an evolutionary stable strategy because this first condition, being the highest in your own column, is fulfilled. If that's fine, I can ignore the second step. Let's look at the second player, B. B gets 1.5 playing itself, which is not the highest in the column. The C player against the B player gets more, 2. So he's not this, the first condition is not fulfilled. Let's look at the second condition. If I am equal than any of these pairs, well, I'm not, I'm lower. So the second condition is also not fulfilled, so I am not an evolutionary stable strategy. He is not an evolutionary stable strategy. Let's look at the C player. The C player now gets 1.2 as a pair of playing itself, and he's not the highest player in this column. Another player gets 1.2. So, if that is the case, I have to check if this payoff down here, the 0.1 payoff, is higher than what A gets against itself, which is also not the case, so C is also not an evolutionary stable strategy. What this means is, if I give you a payoff table, you just follow these rules and you can derive who is the evolutionary stable. If there's only one strategy that is evolutionary stable, there's only one winner. If you have none, that's some kind of mix. And if you have two, it depends on starting conditions. Really easy way to sort of look at these matrices and arrive at a quick solution. You had a question?
What do you mean when you say evolutionary stable?
That means that if you would take this pair, take this matrix and let these players play against each other, then they get differential payoffs, depending on the frequencies of those. If you make their offspring, or their abundance, depending on their payoff, let's say those that get lots and lots of payoff become more and more and more, and those that get lots and lots of few payoff get fewer and fewer and fewer, what you see is that there's either one strategy ending up, that's the evolutionary stable strategy, because over the evolution of this mini-game, these are the ones that win. Or if you have a situation where you equilibrate, then both strategies are evolutionary stable because they're going to survive this game. That's where evolutionary stability comes in. I'm going to discuss this evolutionary part of evolutionary stable strategies in a minute.
Excuse me.
Yeah.
So why do you check this value in the column, not in the row?
I mean, the simple answer is that's how it's defined. Okay. I mean, what you have to do is you have to check. I mean, let's look at the C player, right? The C player gets a certain payoff against itself. Well, how do I fare against all the other ones? Okay, so if I am highly abundant, how does B do against me? Well, it gets less than I do. If there's A players, well, if I am abundant, then the A players get 1.2. They get as much as I get from them. So it's not really clear what happens. And then I have to check how much I get against the A player. And I get less against A players than A players against themselves. And that's why C is an evolutionary stable. For the A player, on the other hand, he is the highest in the columns. He is the one that does best if there are lots and lots of A players. He will win. It's irrelevant what the other ones get in this particular case. Does that answer that? Because you always read this table to the left. It's a little unintuitive, I have to say. In the end, you could sort of write this down and then make the math. Oh, there are more, and then do it. Okay. Now, I said that you can arrive at the equilibrium frequencies of these things. Well, if you know the payoffs of these, then the equilibrium of the payoffs of all these fractions of pure strategies, their payoffs have to be the same. So once you know there's payoffs, you just say that WA, the payoff of the A player, must be the payoff of the B player, and then those payoffs must be the payoffs of the C player. And I only, quotation mark only, have to solve for the frequencies of A, B, and C to solve them. That is still sort of, average math, let's put it like this. Okay, you can do it. If you don't, well, you can just replicate the equations. Basically, you evolve this game yourself, just measure the frequencies of, the payoffs of these, and then update the frequencies and just run the experiment. Rather simple way of doing it. So, these slides have a colored background on the core things you have to remember. As long as X and Y are constants, you can solve and make predictions about these games, either using evolutionary stable strategies or solving these differential equations to find a fixed points. And this is still all doable. Okay. Now, let's look at rock, paper, scissors. Yeah, I mean, it is awkward because the following occurs. This is the payoff table. Rocks get 1 when they play against scissors, papers get 1 when they play against rocks, scissors play 1 against papers, and that's it. Let's check. Rock has a 0, it's not the highest in its column. Rock is not an evolutionary stable strategy. Neither is paper, neither is scissor. Well, we know that, right? If we always play rock, that's coming. Okay. And if you solve this, well, you know that a third is the right solution because they all get the same payoff. What this matrix and this solution says is that if you only have rock and only paper and only scissors players and strategies, the mix of these strategies will be a third of them will be rocks, a third of them will be scissors, and a third of them will be papers. Yeah, but nobody always plays rock. Right? I mean, that might be the solution for the system. Yeah? But strategies aren't always rock, always scissors, always paper. In fact, the best strategy in rock, paper, scissors is to be random. Right? To play the same frequency rock, the same frequency paper, and the same frequency scissors. So I can make a strategy that instead of being always rock, always paper, always scissors, plays with certain probabilities these different things. That is called a probabilistic strategy because this is not a pure one. Okay? If it's a pure one, I could do the simple evolutionary stable strategy stuff. This is a probabilistic one. Well, that's not that good. And on top of that, this game becomes extraordinarily complicated if you play these other variants, right? I mean, what is it? Rock, paper, lizard, rock, paper, scissors, lizard, spock, and then there's this super crazy stuff with two hands and whatnot. Remember, if you want to use evolutionary stability, it's a solution. You still have to look at these matrices, and these matrices can become fairly large. Sorry, yeah.
So I had a question going back to go back just one more. Back.
Just
Right, so here, if rock plays rock, neither win and neither lose.
Mm-hmm.
But if rock plays paper, rock loses to paper, right? So how is that represented with the zeros? Because if you always play rock and I only ever play someone that plays rock, neither of us will ever win,
yeah.
but neither of us will ever lose.
Okay, you can mend that matrix and basically saying rock gets a -1 playing paper.
Okay. So
and let's imagine you put in all these minuses, right? This one should be a minus.
Right.
And then what is it? This one and that one should be a minus. It will not change anything on the statement about evolutionary stable strategy.
Okay.
Because let's imagine there is a -1 down here. Well, rock is not becoming evolutionarily stable because the zero is still lower than what paper gets against rock. So you're right, you can change that, but it doesn't change the dynamics of this game. And it doesn't change this frequency. Okay. So what to do if I wanted to consider probabilistic strategies, right? So far we talked about pure strategies, now let's talk about probabilistic strategies. I can always create a larger matrix, including this probabilistic strategy, by just computing what this mixed strategy gets when playing against rock, playing against paper, and playing against scissors, and what the other strategies get playing it. Because this is the mixed strategy, the row and the column for the mixed strategy will always be the same. Okay? So you can take probabilistic strategies and just add them, and once you have added them, you can use the usual evolutionary stable strategy consideration to solve it. Okay. Actually, that's the summary slide. It says that you can always add strategies that are probabilistic. Okay? And then still solve this. That's what this is called. However, there are lots and lots and lots of possible probabilistic strategies, right? I just added the one that is 50, a third, a third, a third. I could add one that's a sixth, a sixth, and 4/6, or weirder probabilities. Which means that every time I look at a new probabilistic strategies, I have to make this matrix one bigger by the one that I'm looking at. And because they're probabilistic and these numbers are continuous, technically I always make this table infinitely large. That kind of sucks if you want to check rows for am I the biggest, because then you do infinite computations. You can still use math to solve this, right? Because you can approximate what the pairs are, and then you can say, oh, it doesn't matter, I will always be better against all the other ones. Okay. Now, actually, natural systems aren't constant, right? I mean, we looked at situations where everybody gets the same payout all the time. But I mean, you have seasons, you have tides, you have stocks, which actually these are stocks, these are resources, I mean, it's gold and something else. They change over time. If you want to incorporate more dynamic systems in evolutionary game theory and game theory itself, well, you have to change the payoffs pure strategies get, because suddenly they are not conditional on the frequencies of things anymore, but they are bound to outside impacts. They're suddenly dependent on seasons, tides, and those kind of things. Well, that's still fine if you know that, for example, X and Y are always positive or always negative. You can still do the evolutionary stable strategy considerations. However, your solutions that you get are suddenly dependent on these outside variables. And even if you solve these differential equations, you will not find a single solution. You will find a solution that is dependent on these variables. Okay, we still do it. Let's get to a more complicated game, and these are iterated games. So the most famous one is the iterated Prisoner's Dilemma, but there are tons of other games. Okay, I'm just picking that one because it's the most famous. In the iterated Prisoner's Dilemma, you have the following options. You can either cooperate or defect. If both cooperate, you get a payoff of 3. If both defect, you get a payoff of 1. And if one cooperates and the other one defects, the cooperator gets nothing and the defector gets 5. This is exactly the same example in the beginning. It's just different values. The interesting question is now, once we played once, how do we play on the second time? Right? If I already encountered you once, when you say, oh, you're a cooperator, well, I probably should cooperate against you. Or, if you ripped me over in the first move, well, I should continue defecting. Or maybe I should defect on you on the first move and then later apologize by cooperating. You see that there's lots and lots of thought that suddenly goes in there the moment I do more than one game. Right? I repeat this game. Now, the moment I do that, and remember we are talking about probabilistic strategies now, I can assign a probability to cooperate on the first move. It's not just a single always cooperate, always defect. I put a probability. If we both do that, then the second move is not deterministic anymore. It could be a certain distribution of moves where we both cooperated, where I cooperated, you defected, I cooperated, or we both defected. Which means if I want to encode a strategy that takes care of at least 2 moves, the first one and the second, I have to put probabilities in there for all these different tasks. Okay? So I need 5 probabilities for games that remember at least the last move. Okay? Let's imagine I want to make a strategy that remembers the last 2 moves. Right? I could have cooperated, we could have cooperated on the first move and on the second move, or we could have cooperated on the first move and then on the second move I cooperated, you defected, and so forth. You see that the longer I remember, the larger this tree of probabilities become, and the larger the space of variables that I need to describe a single strategy. Remember when I said that adding probabilistic strategies make these tables larger? Suddenly these tables become extraordinarily large when they're already infinite, but they become even larger because you have way, way, way more options. And that comes with one extraordinarily bad drawback, and that is, can you compute the payoffs of these 2 probabilistic strategies? I think the simplest case, the first guy is an always cooperator. He always cooperates in the first move, and then regardless of when that first move happens, he cooperates again. And you play that against the defector. Very easy. The left guy gets 0, the right guy gets 5. Or as often 0 and as often 5 as long as you play. But still, the ratio is the same. Because their sequence is always cooperate, defect, cooperate, defect, cooperate, defect. So left guy is cooperating, the right guy is defecting, and then we just jump to the next step. How about this one? This is the famous tit for tat strategy, and tit for tat is defined by I do what you did on the last move. Okay? If we both cooperate, I'm going to cooperate. If you defected, I'm going to defect, and otherwise I cooperate. Now the strategy is defined by I do what you did last move, so I have to find some way to define what I do on my first move, okay? It's not necessarily defined when I just said tit for tat. So let's assume both players cooperate on the first move. Well, they will continue cooperating throughout the game, because they always do what they did the last move to each other. If they both defected, well, then there's a series of defection. If it's random, let's say 50-50, well, then it's either cooperate, defect, defect, cooperate, cooperate, defect, defect, cooperate, and so forth, or the other way around. Depending on these frequencies, I can at least estimate how often this frequency, this sequence, or the last sequence occurs. If I know this one probability, I can do that. Yeah. Good luck with this example. If you have this example, well, then I have a very, very large range of possible sequences which all occur with different probabilities. Forget it. You cannot mathematically determine their payoffs. Only for very, very small subsets of these things. Well, if I cannot write down the payoff anymore, well, what that means for our consideration with this matrix here is that suddenly you have question marks in this matrix. It's not even external constants that change, it's really question marks. I really don't know what they're doing. Well, that's kind of detrimental if I want to think about evolutionary stable strategies, because evolutionary stable strategies consideration requires that I know the question marks. They're gone. Okay. For certain games, I can still determine the question marks. Rather complicated stuff. Chris can do those kind of things. I can. So, kind of sad. Okay, let's go on. When we get to the evolution of these strategies. When you think about evolution, you should all know that an evolution is requiring inheritance, variation, and natural selection. And we call this whole thing evolutionary game theory, so we should find these three processes in there, right? Well, inheritance is easy. Rocks always make rocks, okay? Fine. Natural selection, well, if rocks play good, the frequency of rocks goes up. That's in there. Variation, not so much, because rocks remain rocks. Like dogs remain dogs, monkeys remain monkeys. If that would be true, it wouldn't be us, right? The only mutation that is allowed in these things are frequency changes. You can say, oh, paper mutates to a rock. Or some kind of magic transformation, maybe some kind of mutation. But really, by just writing down these pure strategies, you prevent mutations from happening. If you prevent mutations from happening, well, then you're violating the second term that's required for you looking at evolution. So, this thing is technically not describing actual evolution, because evolution requires you to have variation. Kind of important, right? This field is established like 30 years as evolutionary game theory, and just told you it's not doing evolution, okay? So, to show you how crazy that approach is the following. Let's imagine, ignore that's a German slide. Imagine all these animals, right, throughout evolutionary history. If evolutionary game theory, the way it is right now, would be able to explain this, you would take all these organisms in the big arena and say, fight it out. Temporal consistency, inheritance, all these changes that happen due to other changes on top of each other, completely ignored. That's how poor current evolutionary game theory describes it. So, what do we do in order to sort of amend that problem? Well, we introduce mutations, which means that we take a probabilistic strategy, and when this probabilistic strategy needs offsprings, there is a chance that one of these probably changes by mutation. Okay, and later it can change again or not. However, I haven't defined how they change, right? If this probably changes from whatever 0.978 to whatever the other number is, I was just drawing from a uniform random distribution. But that's not necessarily true for natural systems. They might not draw from a uniform random distribution. They can have a plus-minus effect on these values. They can be from some biased distribution at high values or more likely than low values, whatever. The moment I apply mutations, I have to incorporate the mutation operator, and that thing has to make sense. Okay, that's not defined by the theory. Let's skip this one. Okay, so I think it's the second last slide. We now introduce the last step, and that is mutational operators. If you have probabilistic strategies and mutational operators, what you have is you have a matrix that contains lots and lots of question marks because you don't know how probabilistic strategies play against each other, at least not a priori when you just look at the probabilities. And you have a matrix that is changing in size all the time because you get new species added and other species die out. And last but not least, who is on the rows and columns as strategies changes all the time on top of it. Because maybe the A prime strategy wasn't around last time, it's just a new one. You have to reevaluate this constantly all the time. So, reasons to do modeling. Where I said you can't do it with math. The only other thing that you can do is computational modeling, or modeling by yourself in your hand. That's not a good option for many things. Okay, so classic game theory is limited to your ability to do math. Like for Chris, Chris's ability to do math. Well, if I do computational modeling, it's only limited to my ability to write code. That's much easier to learn. Okay, right?
Well, in particular, math, it's limited.
It's the boundary, right? So some problems can be solved using classic math. Or they can be used doing extraordinary complex math. But iterated games, variable payoff, complex game, conditional plays, all these things immediately can't be done. And these are the things that are interesting, right? If I do something because you did something else, it's a much more interesting thing than I've always called it. Okay? So, the third one is classic evolutionary game theory ignores variation, should actually be called population game theory. Do that. And lastly, since evolution must contain variation and mutation, you need computation. Okay? think about modeling